So good morning. So my name is Ramy Iskander. So I am the CEO of a company called INtento Design. So let me explain the logo. So INtento means intentions. So this is a new concept for analog design by intentions. And when we say responsive EDA, it means that for the same analog IP, the software will respond differently to each designer. So we prefer, instead of talking about analog synthesis and optimization, we would rather prefer to talk about acceleration of analog design and migration at the simulation level. So the history of INtento is a bit long. It starts from 2008 when I became a professor at Université Paris in Paris. Then in 2012 I started to put patents through my research work. And then I received the public fund to develop the first proof of concept. In 2014 I won a national competition. And I started INtento in 2015. So I founded the company, and we raised around 1 million euros from private and public investors. I hired 5 employees. We are 4 PhDs in this company, in mathematics, in electronics, and in computer science. So in 2016, we were able to put the first version of the ID on the market. And then we delivered the first version to a big institution in France, and we won two other competitions. And now we are starting to receive evaluation requests from many countries, from India, France, Switzerland, Canada, and the US. So here I will explain something very unusual. So why we couldn't do analog synthesis till today? What is the problem actually? So we came up with this diagram, which has 4 vectors. Okay. So this vector is just the parameters that the designer would use to do hand analysis. And this one is the input to a simulator, the widths and the polarizations. And this one is the small signal parameter, and this one is the performance models. So we will try to classify all the ADA tools that are on the market today on this diagram. For example, we have here the SPICE-like simulators. So all kinds of simulators today are the mapping from vector 2 to 3 to 4. This is SPICE simulator. So we take widths and we take polarization and we get performances. So people follow this model from late 80s to develop what we call simulation-based optimizers. So they took these 3 vectors and they put around an optimization engine, and they came up with the simulation-based optimization concept. We see neolinear in the history, we see analog design automation, and many other examples. Okay, but the point is, in the next slide, the designer, when he does hand analysis, he uses these 2 vectors only. So he starts with the design parameters, okay, and then he does something called sizing and biasing. So he writes some equations, and then he gets the sizes and biases, and then he continues. Up to date, we found that there is a lack of automation in this step. Nobody thought before on automating this step. And this is why we don't have real analog design automation tools. Okay? So what we did actually is that we came up with a methodology to automate this mapping automatically. And we are able to automate the whole flow for analog design. Okay? And we came up with an interactive tool which is very fast in sizing, which is deterministic, it's not really optimization, which is correct by constructions, and we can target really speed and accuracy. So how we did this? We developed a constraint-driven design methodology, and we imagined that this methodology should be a structured design methodology. It should be based on designer-specific constraints, and it should fully respect circuit physics. It should bridge the gap between hand analysis and SPICE simulation. It should handle complex circuits, and it should allow full insight in the design space, graphically, for example. And as a result, we will have a fast, interactive, deterministic, correct by construction. So is it possible? Yes, it's possible through our product. So we came up with a product called ID Explore that will take the unsized OpenAccess database schematic. It will take a set of constraints like design, technology, and performance constraints, and the designer will specify the set of parameters he would like to control on the schematic, on each transistor. And out of this, we will create, our software guaranteed to create what we call a structured design graph, we will assign to each transistor a primitive. Okay, this primitive, you can see it as the logic gates in the digital domain. So it's the equivalent of this is the equivalent primitive for analog. So we can put as a Lego, and the design parameters will appear at the beginning here, and it will map all the knowledge or the model to get directly the widths of each transistor. So once we create this model, we just put the values of the parameters, and with one iteration we get the widths. So it's very fast to generate this model, and it's very fast to evaluate it in one iteration also. But the point that we discovered also that this model is the same for all topologies. If you have the same design parameters, we'll have always the same model. We need only to switch the design kit that is integrated directly for these primitives to size the same IP for a different technology. So let's say we can generate this model in only one time in the history of the circuit actually, and then we use it in different technologies. So I will give a real example. So this is the Miller OTA amplifier. We have set design constraints. We would like to eliminate the offset here. So we had set some constraints, and we had set some technology constraints on the length and the width of the finger, and we have set some constraints on the performance. And we specify which parameters we would like to control. Some of them are fixed, and some of them are variables. And this is the real graph that we get in memory actually. So we have these design parameters here. These were on the table. And for the current mirror, we assign a primitive. For the differential pair, another primitive. For the biasing current, another primitive, and so on. And we connect them based on the constraints the designer had set. And we come up with the widths on each primitive here. This is the width, the width, the width, the width, and so on. So this graph has lots of properties. Among them, I would say that this is the design viewpoint of the designer. I mean, the designer has specified a set of parameters. He got this graph. But if another one has changed the parameters, he will get another graph. He will not get the same graph. So in this approach, there is no convergence problem, because we managed to have convergence, always to converge on each of these primitives. We have a mathematical approach that we are only using monotonic functions. We are resolving two problems in analog, but both of them are linear. And this way we don't have a convergence problem. But we have another type of problem which calls the coherency problem. The values that are supplied to these parameters may be conflicting. For example, if we put a small VGS for a high current level, but this is not a problem, it's a good news. Because if we have an operator that doesn't converge, we know exactly which parameter.
Now exiting.
Has the cause of convergence. So we report this directly to the designer. So we know which transistor has caused the convergence issue. So to appreciate a little bit the method, this graph was generated in 100 milliseconds, and it is as fast as a SPICE simulator in a commercial simulator in terms of DC computation. So in this type of solution problems, we have three different problems. We have the well-specified design. This means that the number of the design of parameters are exact. Under-specified, this means that the designer has specified less parameters than he needs. So in this case, we can it creates some topologies in the graph, and we know which set of parameters are involved, and we can report it to him. The same way, if he has over-specified design, it creates excess number of design parameters, which is some pattern in the graph where we detect it and we report it to him also. So once we have designed the whole flow, let me present a real example that we studied. So we designed a GMC-based Fourier configurable filter for multi-standard communication. So we took each step and we evaluated the number of days. We suppose 5 days per week. So for schematic and test benching, we got 1 week. For the sizing by successive simulations, we got 3 weeks. It was a little bit a hard design. For layout placement and unlocking, we got 4 weeks, and 1 week and 2 weeks. So in the best case, we will get 11 weeks. But due to these iterations, we can really be stuck with this design. So what we did is that we have cut this iteration and did the direct mapping through the graph that we created. So the 3 weeks here vanished. So we put, instead of 3 weeks, you got 1 day, because we did the graph was scanned from this very quickly. And then we added 1 day for the design constraints that we have added. So we had a gain in time and cost 65% in the first design phase. If we compute for the whole flow, it will be around 30% gain. We applied the same technology in analog migration. So instead here of 1 week getting everything done, we came up with an idea of constraint migrator. It will take the knowledge of the source OpenAccess and it translate it to the database, the target technology. And then the 1 week has vanished also. So we gain 90% in the first phase of the migration. And for the whole flow, it will be also 30%. So I will show some snapshots for ID Explorer, how it looks like. It's maybe not very clear, but this is a VGA, this is a client case where we got, it's a variable gain amplifier in a transceiver. So there is a channel connected in the differential input here, and then the VGA should compensate the channel loss. So we added some symbols here. These are the annotations that we add on the schematic as the constraints. So for example, here we defined a set of global constraints, global parameters on this symbol. And then we map this set of parameters on each design. For example, on each transistor. For example, we need to match these 4 transistors together. So we will select all of them, and we will set the same constraint for them. So we have what we call a reference transistor, which will be sized and biased, and the rest of transistors will inherit all the characteristics from this transistor. So we can set very quickly the constraint graph. And then once we are done with this, we just go into ADXL. We specify some constraints and some objectives. Once we are done with this, we save everything in OpenAccess database, and then we move to our ID Explorer. We have a library manager. We open, we select the design. We check parameters. It means that we build the graph here in this step. So if the graph was well designed, all the parameters will be checked. So once we generate the graph, we get the list of parameters here. We select some of these, and we select some minimum and maximum for the design range. And then in the second phase, we just import. We just press the button import. It will fill out this table automatically. We will import all the constraints from ADXL, and we fill this table. We also choose the simulator. Now we are 100% compliant with Spectre. We will choose the design kit through a file, and we will set some technology constraints here. This is the finger width that we would like to apply on the whole design, on the whole transistors. And we can modify maybe some values here. And when we are done, so we just launch our ID Explorer engine. So we have the full mode, the global and local mode. A global, it means that we ask the simulator to give us the best 10 solution in the design space. So it displays the best 10 solutions, okay? And it's up to the designer to interact with these solutions. For example, he would select this one and do a local refinement. So he will get, for example, this solution, okay? He can go further and select another solution, okay? And then he will get local refinement, he will receive another solution, and so on. But the idea here is that this solution, for example, was not fully specified, was not fully satisfied. We have here 2 red constraints, but we expect after the local refinement that the solution is refined. Okay, and so once we select this one, we get the widths and we get the number of fingers for each transistor, and then we back annotate directly to cadence environment. So in the schematic, and we can simulate by ADXL. But the closing point here is that we have to have
now exiting. Name not recorded.
When we simulate with ADXL, we have to have the same results as here on the specs. If we don't have the same results, it means that something went wrong in the flow. So once we are done with this step, we are sure that everything is okay, and we have successfully designed the analog IP. So what are the features about this? There are benefits for companies. We can reach 60% of cost and time saving. We have a fast time to market. We allow more business opportunities. And we protect the IP portfolio of the company. And we can standardize exchange between design teams. and the analog IP becomes an interoperable entity actually. For designers, actually, we hide all the technology details from the designer. He doesn't go. We saw some designers looking into the design kit to get to maximize the effective mobility, to get the maximums. I don't know what, but these kind of things with the PVT fell down, doesn't work. So we feel that the designer should not go in deep into the design kit. We automate all the tedious work, and we have a GUI design, this GUI, to have the minimum intervention of the designer. Once we are out of cadence, nothing can be changed. Nothing can be changed. And you can just several concepts. I would like to say also that today we are fully compliant with existing design environment. It's fully compatible with OpenAccess. And we have a linear scalable multi-core search engine. We can deploy the sizing on several cores at the same time. And this is transparent for the designer. There is nothing to do. We detect the number of cores and we deploy it on all the cores. And the most important is that we are compatible with all design kits and with all type of devices, like CMOS, SOI, LDMOS, and FinFET, and we can do FD-SOI also. Thank you, and this is, so we designed this also. So if you have any questions.
Questions on the phone? Questions here?
No questions.
I'll ask a question. So analog design covers a lot of ground. What areas of analog design do you expect will be applied to first? With
all types of analog IPs, we tested
RF or
RF. We can deal with RF, but with ideal models, because we don't have a synthesis of inductors. This is the only thing that we don't have. But we can deal with any type of block, like DC-DC converter, power converter, amplifier, band gaps, any type of. We tested on different types of analog IPs. The only thing that we don't have is the inductance synthesis actually.
Thank you.
I have a question if no one else does. So, in the case you're over-specified, that's a trade-off to runtime, I assume?
No, in over-specified, it means that the designer gave more information than usual. So there are conflicting hypotheses.
Okay.
So we tell him.
Where in the flow do you get that feedback?
I get it here. We report it here.
Okay.
For example, I will show you an example. For example, here. For example, if you would like to have an offset voltage here, which is not equal to 0, it means that the potential here and here will be different. Okay. In this case, we report to the designer that there is an excess number. No, there is a lack of design parameters. No, there is an excess because he has specified, for example, VGS different than VDS, and we tell him you have to remove one of these two parameters actually to be compliant with the design. Okay. Or you have to generate an input offset voltage.
All right. Any other questions? Questions on the phone, you can unmute with *6. If not, we can go on to the next. Jason Singh is going to present IPscape.
Here's a PDF.